So suppose you have two propositions. Well, okay, first suppose you have one proposition, and then we'll introduce the second one. Phi, here's our placeholder for a proposition. What could possibly be the case? So according to excluded middle, either phi is true or not phi is true, right? So that means there are two possibilities for phi. Either it's false or it's true. Those are the two possibilities. There's nothing else. Either it's false or it's true. And it couldn't be both. Excluded middle doesn't disallow both, but the fact that both would be a literal contradiction is disallowed by proof by contradiction. So phi is either false or it's true. Now, what if you had a second proposition and you were thinking about both propositions together, and what could possibly happen with these propositions? With each proposition, it's either true or it's false, thanks to excluded middle. So there are four possibilities then. You could have either phi is false and psi is false, or false true, or true false, or true true. And if you have three propositions, then you would have 8 possibilities, and so on. So given any number of propositions, thanks to excluded middle, you can list the finitely many possibilities as to their truthhood or falsehood. And what I'm about to show you is called a truth table. So you can use this list and make up the rows of a table, and then fill in the rows of a table various bits of information. So, for example, let's suppose you were wondering about let's suppose that you're wondering about, in each of these situations, what is phi and psi. So phi and psi, it's a proposition, and it's either true or false, right? So there are just the two possibilities. But can we describe in each of these situations whether it's true or false? So what if phi and psi are both true? If phi and psi are both known to be true, then according to the rules for AND, we can deduce phi and psi. So it ends up being true. On the other hand, if either phi or psi, if either of them is false, then we cannot deduce that one, and therefore we're blocked from deducing phi and psi. And in fact, you will see that we end up getting false in all cases here. So let me just show you quickly how you might justify one of these rows of the truth table. So let's suppose phi is false and psi is true. Then can I justify this conclusion that phi and psi must be false? I claim that I can do this using proof by contradiction. And here's how that might work. So assume that phi is false and psi is true, meaning assume not phi and psi both hold. Right? Not phi, to assume that not phi holds is to assume that phi is false. That's what false means. Then can I prove that phi and psi is false? Yes, by contradiction. Suppose, for the sake of contradiction, that phi and psi holds. Now, I'm assuming the opposite of the thing I'm trying to prove. I'm trying to prove that it's not the case that phi and psi. Now I'm trying to get a contradiction so that I can finish this proof by contradiction. So from phi and psi, I can conclude phi why? This was one of the rules. it was this rule. When I have phi and psi, I can deduce phi and I can deduce psi. So in particular, I can deduce phi. Now I have not phi as one of my assumptions up here, and I have phi. This is a contradiction, right? Therefore, phi and not phi. I can deduce this because, again, one of the rules for and, I have this and I have this. Therefore, I can deduce their conjunction. You can see that here, this rule. I can prove a conjunction by proving the two components. So now that we've reached a contradiction, the proof by contradiction lets you conclude that what was assumed must be false. So suppose for the sake of contradiction that phi and psi, blah, 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 I reached a contradiction. Therefore, it's not the case that phi and psi. So that's where this false is coming from. So filling in this truth table really comes from arguments that use the rules of logic that we've established. So you could similarly establish these other falses and this true using the rules. Now let's look at what the rules for OR look like. Or rather, what the truth table entries for OR look like. So let's put phi or psi here and fill in what we get. So let's just think intuitively first. Well, I guess this is not intuitively, this is just straight up following the rule. If you know that phi is true, like in this third row, then you can deduce phi or psi. That was one of the rules for OR, so it's true. If you know psi is true, similarly. And also, in the case that they're both true, you know that phi is true, so you can deduce phi or psi. The fact that you also have a second proof that phi or psi, one using the fact that psi is true, doesn't really add anything to the picture. Now, what if you know that phi and psi are both false? Can you conclude that phi or psi is false? I'm going to say yes, and this one you might want to pay attention to how to justify this. So let's see what might go into proving this row of the table. So to run this argument, to justify this row of the table, I need to assume that phi is false and psi is false, so assume not phi and not psi. Then I want to prove that phi or psi is false. So I'll suppose the opposite. I'll assume the opposite for the sake of obtaining a contradiction. So suppose for the sake of contradiction that in fact phi or psi is true. Where am I going to get a contradiction? So I'm now in a situation where I know that a certain OR statement is true, and I need to make use of that fact. How can I use that fact? Well, in case you ever forget, just check the table. Here is my table, and under OR, if I want to make use of an OR fact, I have to use proof by cases. So here there are two cases driven by this OR that I have. So this is a proof by cases inside the proof by contradiction. Case 1, suppose phi, and case 2, suppose psi. Now, in case 1, since I have phi, and I have not phi from above, there's my contradiction. Then phi and not phi. And let me put an exclamation point to indicate, hey, we reached a contradiction. So the proof is done in case 1. The proof is done because we reached a contradiction, and therefore we must deny what was assumed here for the sake of contradiction. Case 2, suppose psi, then psi and not psi. And there's our other contradiction. So in all cases we reach a contradiction. Therefore, using this proof by cases idea, assuming this just leads to a contradiction in every case. So we must reject this. And that's the justification for this false. Okay, so we've looked at how and or appear in terms of truth table information. And this is just a really nice, the truth table is just a really nice thing to keep in mind to understand how the logical connectives and or work. Not has been left out here. Let's put it in. It's very simple. If phi is false, then not phi is going to be true. And if phi is true, then not phi is going to be false. And that's sort of due to the way we defined the word false. We said for a proposition to be false is just to say that its negation, its not, is true. And we also said that not phi is the same as phi. Now let's also look at not psi in this situation. If psi is false, not psi is true. If psi is true, not psi is false. And then same information here. Then, now that we've filled this in, we can actually examine more complicated things. So, for example, what would you say about not phi or not psi? Like this. Well, the way an OR works is you end up getting, we already examined the truth table for OR, and we saw that you end up getting a true if either one of the things are true or both, and a false when both of the individual things are false. So here we have true, true, so true. True, false, so true. False, true, so true. And then only in this case where they're both false do we actually get false. So now we have, looking at the overall truth table, we kind of have this nice mapping from truth values for the individual phi or psi to truth values for this more complicated logical expression here. If phi is false and psi is false, then this thing ends up being true. It's fun to put actual English sentences in place of phi and psi and think about how this works intuitively. So here's an example. Okay, let's try this example. Suppose phi is I have a cough and psi is I have a sore throat. Then let me just pick a row of the table and analyze it. Let's suppose I do not have a cough, no cough, and I do have a sore throat. Then what does this say? So this would say either I don't have a cough or I don't have a sore throat. Either I do not have a cough or I do not have a sore throat. In a situation where I do not have a cough and I do have a sore throat, it's definitely true that either I do not have a cough or I do not have a sore throat, because I do not have a cough. Hopefully that makes some intuitive sense. Okay, so now I want to look at phi and psi, just for fun. Let's fill in what this was again. False and false led to false. False and true led to false. True and false led to false. And true was the only way to get true. And then I want to look at the negation of that. So not phi and psi. So that would be basically take what you see here and then negate it. In the case that phi and psi is false, not phi and psi ends up being true. False goes to true, false goes to true, true goes to false. And the point of looking at all those examples was to observe this interesting matchup here. That in all situations, in all cases, whether you have false, 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 true, true, false, or true, true, in all cases, you get the same outcome for these two different expressions here. So that suggests to you that, in some sense, these are the same. Not phi or not psi is somehow the same as not phi and psi. Now, the exact way in which they're the same, we will make more precise later on. But I hope for now that you can somehow make it intuitive to yourself that they're the same. So let's go back to phi being I have a cough and psi being I have a sore throat. This would say either I don't have a cough, let me speak more clearly, either I do not have a cough or I do not have a sore throat. On the other hand, this would say it's not the case that I both have a cough and a sore throat. And I hope you can get an intuitive feeling that those really are the same thing. So a truth table is one way to see that two complicated looking propositions involving logical connectives are actually the same, or to check whether they're different. Now, all that being said, the truth table really is a temporary tool that we're only going to look at briefly just to help understand how some of the logical symbols operate. So it's a helpful tool for understanding, but we're never going to use it to ever prove anything. So when we write proofs, we want to convince, right? We want to convince a human. So we want to write paragraphs that use arguments and that rely on the deductive rules that we laid out. Things like proof by cases, proof by contradiction. That's what you will be using in practice throughout the course, and almost never truth tables.